Yes.
Okay, good morning, everybody. I hope you didn't take decaf, but I'll try to do my best to make it a reasonable presentation. So I shortened the title to Beyond Land Cover Changes because since I submitted the abstract, we kind of expanded a bit on the topic. First of all, I will do the talking today, but that does not mean that this is my work. This is the work of a group of people, and most of them are here today. They're somewhere sitting in the middle, out on a row. So there is Julian Otto, James Ryder, Kim Nance, Matt McGrath, Aude Ballade, and Ying Sheng, who contributed a lot to this work and who are working on this project. And then I got a lot of discussions and inspiration from and help from Mathilde, from Paul Stoy, from Julia Pomgratz, and from Karl-Heinz. So if we're talking about land use in an Earth system context, we most often reduce the whole concept of land use to land cover change. And in most of the model, land cover change nowadays is included, but it basically means that we distinguish a certain number of discrete land covers, like a forest, a grassland, or a cropland, and we model what happens if we change from one to the other. However, if you spend some time on the train or in the car and you drive through a landscape and you start thinking about what you see, you will notice that it's not a discrete change, it's a continuum. So you can start with a forest, and then at one time the forest is not, it does not yield enough, so you add some cows and the cows start grazing. And there is some interaction between the forest and the cows, and then you don't have enough trees anymore to consider it really a forest. That's like maybe this is the pointer. Yeah. So then at one point, like the cows, they eat the seedlings, and so the forest, it gets more and more open, and you get in like a open type of landscape where there are not enough trees for forestry and there's not enough grass for farming, so you have to take a decision whether you return to the forest or you go further and you add more cows, you remove the trees, and you end up with a real grassland. And this is more what has been happening, or this is what is happening, and it's still happening for today. So for that reason, I introduced like a new term. I'm not claiming everybody should adopt the term. I just introduce it to make a distinction during this presentation between land cover change, which means that we change the vegetation, it's a forest, grassland, cropland, and land management change, which is a change where we keep the cover. So we have one forest, we cut the forest and we plant another forest. Or we have a forest and one objective could be to grow tall trees, or we just keep the forest and the objective is to grow biomass in a short rotation cover. So the cover has not changed. It all remains forest, but it's very different types of forest. Or we have an extensively grazed grassland. We decide that we put a fence around it and we add a couple of hundred of cows and we start fertilizing and we move to intensive grassland. So these are changes, it's still grassland, but a lot has changed. Or we can fertilizer and irrigation. And this is where the whole definition thing becomes a bit more fuzzy, because irrigation and fertilization are more and more included in the Earth system models. So we use it, land use or land cover changes, and we do part of it. So we do the clear changes from forest, grassland, croplands, and there is an increasing interest in irrigation and manure. But all of these, this far, have basically been ignored. So if we talk about management changes, it's hard not to say anything about intensity. And there's a lot of confusion about intensity, and depending on who you talk to, they will use different definitions. And it's just a matter of perspective. Like you can define intensity in terms of input, how much labor you put in there, how much fertilizer, or how much euros, dollars, like the expenses you make to grow a crop. It can be output, how much you yield in calories, in grams of carbon, or euros, dollars, whatever. It could be ecological, like if you change the vegetation could be more efficient in harvesting light, or it could just have a higher harvest of light. And this, the red box, this is, I think, the perspective that we usually follow more in the Earth system context. is we're interested in the change in the biogeochemical cycles or the biophysical cycles. So if the management type is more intensive, it means that we expect that there is a bigger change in one of these. So hopefully all the definitions, they kind of get us on the same line and can confuse most of the, or can avoid most of the confusion. But it doesn't mean that we're not clear in the definitions and that there are processes happening in the real world that are not included in the models, that they're important and that we should make them a priority. So that's the next part of the talk. I would like to go into this and discuss whether we should make this a priority, whether we should invest time in this. And it's clear, I think, the classic approach of thinking of Earth systems and Earth system models is that we're interested in the climate, and more there's some more interest in the socio-economic services. So if we implement land management in the classic way, the question is that, okay, if we change the management, what will happen to the water balance, energy balance, carbon balance, what will happen with the climate, and what will happen with the services we can provide? For the moment, I think there's not much support for this reasoning, because the common thought is that land management, and then let's say we change one forest for another forest, that the impact of land management is expected to be very small. So this is probably, for the moment, there's not a lot of support for running the models in this direction. But we can invert the process, and we can think of, okay, we want to stabilize the climate. And so what type of management do we need for this? Do we want our short rotation compass? Do we want to have it in the south of Europe? Or do we want to have it in the east of the US? What will happen if we plant sugarcane in one region or forest in another region? So we can start thinking the other way around. And I think for that perspective, it is worth to try it. And so that's what we did. We started looking, and we checked whether we have scientific evidence to make it worth the whole effort of including land management in Earth system models. And so the first place to start looking is, I think, it's field observations. So we used the observations from FluxNet, and we selected sites for which have all measurements for the energy budget, and then they should have been like a cluster of sites not too far apart from each other. And then there were some additional criteria. So in the end, despite that FluxNet nowadays, it is a quite impressive collection of sites and data, we could only use about 20 sites and about 30 site pairs. So we paired the sites, we compared the sites, and when the land cover was changed, we classified them as a land cover change, not surprisingly, and if the land cover was the same, we classified them as a land management change. Whether the management was deliberate or not, we don't know, but it means that you compare two forests and you see what potentially the effect is between, or what the differences are from one forest to another. So we got some sites from Europe or from the US, but I think you figured that out yourself. So then we just looked at the data, surface temperature. We got surface temperature from radiometer on the sites. We have the blue line, and the blue line is the land cover change. And we have the red line, and the red line is the land management change. We just ranked them from the smallest effect to the largest effect. And then we smoothed it with some like a statistical function so that we could create like a distribution. And I think the first conclusion, or what's evidence from this small analysis, is that it seems that the effect of a land cover change is very similar to the effect of a land management change. So there's two conclusions. Either land management is important, or our classification is really bad. It means that the variation within a group is identical to the variation between groups. So the way we grouped it doesn't make any sense. So we looked a bit further into those data, because it was somehow a surprise and we wanted to find more evidence. So the first thing we did is we continued with the FluxNet data, and we looked if we could see some correlations. And one correlation we found is that if the albedo is increasing, then the surface temperature is increasing. And this was a surprise, because you would expect if the albedo is increasing, the surface is brighter, So you expect that more energy gets reflected, and so that the surface would be cooler. Whereas here we see exactly the opposite. So we were not too sure about this. We looked whether this could just be side effect, because it's always easy to criticize the work on the site level, and especially if others have done it, and we haven't done the work ourselves, so it was like a good place to start looking. But then we looked into MODIS, which is of course beyond any doubt that it's error-free. So we looked at MODIS and we selected 9 regions globally where we thought the climate was identical, that the vegetation was identical, but that there just happened to be an administrative border. And here, if you're really good in geography, everybody will recognize immediately that this is the top of northern Finland, and this is Norway. And between Finland and Norway, there is a reindeer fence. And the only difference is in the management between this reindeer area and that reindeer area is that they're allowed to graze in a different season. And so this region is 50 by 50 kilometers. And so you can already see that the Finnish side is warmer than the Norwegian side, because due to the grazing, there's less lichens at the Finnish side. So we did this for 9 regions that we kind of handpicked globally, regions where we knew that this situation occurred, like the administrative border, and we could reproduce the signal. So we also found that a change in albedo in MODIS resulted, or an increase in albedo resulted in an increase in surface temperature. So we thought this was, at this stage, like enough evidence to start thinking about putting land management into the models. And so we kind of made a checklist, and the first was, okay, we have land cover change, we have land management change, and it seems that the effect at the square meter at the site level is very similar. So if that's true, we should treat them equally in our models. And the second question is, well, maybe land cover changes are a lot more important. They happen all over the place, and maybe land management is restricted to very small areas. So we did some kind of, I'd say, half an analysis. It's not a proof, but it kind of suggests the possibilities. Like if you take a global map, you exclude the areas where there is hardly any management, which are the green areas, and then you look at the areas where we already had a land cover change, which are the darker areas. And there's still a lot of land left, where for the moment we can expect some intensification or extensification of the land management. So I think in terms of surface area, there's no problem. Both are important. But then the last thing we kind of considered is that in the last decades and even centuries, the land cover change has often been in the same direction. We lose forests towards other uses like grasslands or croplands. Whereas for land management, it can be more complex. We don't know in which direction it's going. The last 100 years, we went from a very intensive land use in like the 1700s over Europe, kind of gave it up thanks to fossil fuel burning. We moved to like a lot more extensive land use. And now, thanks to too much fossil fuel burning, we're probably going back to a more intensive land use to produce biomass. So we have some cycles here, and so we don't know if this is all going into one direction. But if you don't know something, you can investigate it. That's what we're, I think, being paid for, so that's what we started doing. We had a look at Orchidea. The name of the model has disappeared again. So we had a look at LMDZ Orchidea, which is a coupled land surface to atmosphere model. And this is the flow chart of the model. I don't like these graphs myself, but I think you can't give a talk about a model without showing like a graph with boxes and arrows. So I'm sorry, but the key message I would like to show with this graph is that in black you see the current version of Orchidea LMDZ. And we looked into the code and we started thinking, is this model fit for what we want to do? Is this model up to the task of including land management? And every red box and red arrow you see, it's a moment that we said, no, it's not. So we changed the photosynthesis, we changed the carbon allocation, we thought the way it dealt with water stress was not very physiological, so we added some parts on the water stress. Then we thought, well, the water stress, it should feed back to the photosynthesis in a more direct way, so we have some stomachic control there. And then I think one of the key boxes in this whole story is that when you manage a vegetation, basically all you do is you change the canopy. Either you have some cows, they remove some grasses, and you change the canopy. You thin a forest, you remove trees, and you change the canopy. So we cannot do this as long as we assume that the canopy is a big leaf canopy. So we invested some time and a lot of lines of code into introducing a canopy structure. Once you have a canopy structure, it becomes a different story, because it doesn't make sense to have a canopy structure if your albedo scheme is not fit for it. So we added a new albedo scheme based on the work of the GRC that can account for the canopy structure, uses effective LAI. And then, well, if we have the albedo, why not changing the energy budget? So, well, we changed the energy budget. And so, in the end, we end up with almost like a new version of Orchidea. And I think in terms of lines of code, it's not excessive to say it's half new. There were 28,000 lines of scientific code. We deleted 13,000 of them, and we've written 37,000 new lines. So I think it has been a massive effort in getting from the black scheme to the red scheme. What is still a little bit stressing me out, and I think also like the people on the row who are working with this version, is that we don't know whether it was really worth the effort or not. So we took a high risk here. We just went in, did the work, and now we will see if it was worth it or not. So the graph is not very, or it's very dark, but here you're supposed to see like a green box which shows the way a canopy is represented in the current versions of Orchidea LMDZ. It's a big leaf canopy, it's one box, and even this box is a bit overly optimistic because it has dimensions, and in reality, like the way that albedo is calculated does not make use of any dimensions of a canopy. So it has a mass, but it is dimensionless. So we changed that, and we added real trees, and hopefully here you can see some small trees and some taller trees, and this is a view like a bird angle view from the top, where you can see that now we're starting to have some shadows within the canopy, and we're having structures within our forest canopies. And then, like an extra slide on the albedo is, once we have a canopy, we can start to distinguish between the albedo from the canopy, from the vegetation elements, and from the background. So I think we had a presentation yesterday with the same principles from the shrubs in Siberia. So we kind of introduced these principles, and then so when we have snowfall, we have patches of snow, and the patches of snow, they increase the albedo of the soil. So you can see that it's a lighter soil here. And then when the snow is aging, the snow itself is getting darker, so we still do the same averaging, and then like the background albedo increases compared to this one, and it decreases compared to that. So we think this scheme is fit to account for this type of situations, where you have like bright backgrounds and dark vegetation elements. So some first tests of different parts of the model. Not all tests are made with the full model, but we can start seeing that if we use this albedo scheme and we add management, like forest management in the model, and we go through thinning cycles, which you can see with zigzag. So now this is reflected in albedo. And although the changes are quite small, it's like 2/100ths of a unit. It is for albedo. It is not insignificant. It's small changes in albedo can have quite a big effect on the surface. And so then we also continued a little bit with the data analysis that kind of triggered part of this story of the FluxNet sites. And if we look at the FluxNet sites, we see that the change in surface temperature due to change in albedo, it has a negative correlation with the change in surface temperature due to a change in sensible heat. And this is a bit strange. It's not what we expect. And at the same time, we see hardly any effect for latent heat fluxes. So it's a bit contrary to what is often written in textbook or what you often find in analysis. So we didn't feel too secure or too certain, or we weren't too certain about this. But now that we have a new version of Orchidea, where we also have like the dynamics of the canopy, we run the version of Orchidea with the new canopy structure and exactly the same old energy budget. So this is accepted textbook physics. There is nothing special in the physics there. We only changed the canopy. And what we see is the red here, well, the color code has changed, but the red here is the sensible heat flux. So in terms of sensible heat flux, now with Orchidea, we can reproduce this trend without any tuning, without any special tricks. It was just like off the shelf, we put it in there. And well, not off the shelf is excessive after all those months of model development, but so we just took the model version that we're at now, and we can reproduce for both, for sensible and latent heat flux, and we can reproduce the relationship between albedo and surface temperature. So another thing that we considered important if we want to move simply beyond the land cover changes is we have a focus over Europe, and we would like to contribute to the discussion of forest management. But forest managers, they don't manage PFTs. They don't manage some kind of evergreen needle trees. They manage pines or spruce or a specific species. So we're lucky that we had a couple of ice ages in Europe, and especially the last ice age that reduced the biodiversity in Europe a lot. Then a couple of generations of foresters, and so now we can describe the 80% of the forest area in Europe, we can describe it with 7 tree species. And because 7 was not enough, we separated between boreal and temperate, and so we duplicated some species. So we have a set of parameters for the boreal pines and spruces and birch, and we have another set of parameters for temperate birch, spruce, and pine. And so then we can start seeing the first results. The black line here is if we run the new version of Orchidea without forest management, here the same, and the blue line is with forest management. And then for 2 species, Scotch pine and Norway spruce. And then, well, kind of happy, you see that the canopy of Scotch pine is lower than the one of Norway spruce. You see that it takes longer for Scotch pine to get to the point where it's economically feasible to harvest. For spruce, we reach that point earlier. So this is basically where we are at now for the moment, is that we have the species, we have the canopy structure, we can start accounting for management within the model. So we miss one key piece of information, is that we have to spin up the model, we have to start somewhere, and we need to describe forest management. So that's the task, one of the tasks we're working on now, is we're trying to reconstruct forest management for the last 400 years over Europe. I don't need to explain that that's not like rocket science to do it. It demands a lot of creativity, which is kind of fun, and a lot of assumptions. And you try to make the best out of it based on some data you have, some data sets you have, some anecdotal evidence from a monastery in the 1700s, and that kind of stories suddenly become true like all over Europe. But so we're making a map, a demand map that accounts for population, charcoal, like the use of charcoal, iron melting should be in there, like salt production was important, and of course fuel wood. So these are like the demands that we had before the 1850s, and then once we got like the industrialization, we started using different information. So we want to make these demand maps which could also be used by other modeling groups who are interested in working over Europe. After we have this part, when we add in the supply, it becomes more model dependent. So this is becomes more specific to what we do in Orchidea. So that brings me to the conclusions. And based on the analysis we did, I see no reason why we should keep continuing to separate between land cover changes and land management changes, and why we should reduce the whole question of land use to only land cover changes, because the effect seems to be the same. Then for several regions in the world, despite what we heard in the trade talks, I agree that for many regions it's not possible, but for some regions, like Europe, it's perfectly possible to just go at the species level. It's not an excessive amount of work. Then, for many of the regions, and especially the regions with few species, the parameters and the data, they are available. The only problem is that the current models are conceptually and structurally, they are not fit to deal with this question. And so I would say if you have 130 person months, that's what we spend on it this far, which is in France, because we have shorter weeks, 19,760 hours of person months and time. I see no reason why we should not try it. And so that's what we did, and I hope that next time Julia organizes a session that she can invite me for the second part of this talk. Thank you.
Thank you, Sebastian, for this interesting presentation. Maybe I will open the floor for questions. I have one here.